In this video, we're going to see about speed control of induction motor using vector control method, which is known as field oriented control. And myself, B. Rishi Welcome. And this is the outline of the project. And the first is introduction of the motor, and the second is controller used in the circuit, and third is the working of the circuit, and fourth will be the subsystems in the circuit, fifth will be the resultant analysis. Introduction. The motor which works on the principle of electromagnetic induction is known as induction motor, and it is most commonly used AC electric motor. In an induction motor, the electric current is in the rotor needed to produce torque, which is obtained from electromagnetic induction from the rotating magnetic field of a stator winding. The rotor of an induction motor can be a squirrel cage or a wound type. Induction motor are also called as asynchronous motors because they operate at a speed less than their synchronized speed. The induction motors are cheaper at cost due to the absence of brushes, commutators and slip rings, and it can be operable in any environmental conditions. Controller. Vector control is also called as field oriented control, which is a control method in which stator currents of induction motor are identified as two orthogonal components that can be visualized as a vector. The control is based on the projection which transforms a three-phase time and speed dependent system into a two-coordinate time invariant system. The field-oriented control machines needs two constant input as a references: torque producing component and flux producing component. Torque producing component is a quadrature axis component and flux producing component is a direct axis component. As field oriented control is simply based on projections, the control structure handles instantaneous electrical quantities, hence it makes the control accurate in any working operation. And this is the structure and circuit design of field oriented control system. And the field oriented control consists of a space vector projection. The three-phase voltages, current and flux of AC motor can be visualized in terms of complex space vectors. With regards to current, the space vector can be defined as follows. The stator currents of A, B, C can be assumed as IA, IB and IC. Thus, current space vector depicts the three-phase sinusoidal system. It still needs to be transformed into a two-time invariant coordinate system. The transformation can be split into two steps: ABC to alpha beta, which is a Clark transformation, and alpha beta to DQ. In ABC to alpha beta, which has Clark transformation, the output is two coordinate time invariant system. Time invariant in the sense the output will be changing with respect to time. And in Park transformation, the output of two coordinate system will be time invariant. It means the output will not change with respect to time. And this is the space vector projection of the stator currents A, B and C as well. Working of the circuit. The system is designed to drive a three-phase AC induction motor. The inverter converts DC power at required frequency and amplitude, and it consists of three half-bridge units where the upper and lower switches are controlled complementarily, which means that upper one is on, the lower one will be turned off and vice versa. The output voltage is created by using PWM technique. The reference speed is assumed as 500 rpm, and the reference speed and the actual motor speed is compared to obtain torque such as TE value, and ID is calculated by using the reference flux as 0.96 and IQ is calculated by using the torque and flux values. The rotor position theta is calculated for ABC to DQ conversion such as Clark conversion. An inverse Park transformation converts the stator voltage space vector back from DQ to DQ coordinate system to two-phase system fixed with the stator. By using the space vector modulations, the pulses are generated such as three-phase voltages generated to run the motor. And these are the input parameters that used to form the circuit.
Now let's see the circuit part of induction motor. In order to get the induction motor, we have to take a synchronous machine and set the preset values. These two squirrel cage and reference frame as stationary. And we need an universal bridge. This universal bridge acts as a three-phase inverter to the motor. Let's invert this and set the values. These two IGBT. and forward voltages to forward and this to 0.75, and we need a DC input source and connect to the and set the voltage to 500 amplitude. Now let's see about subsystems. And select an input port and copy that, paste here, and select for an add block and select a PID controller and an output port. Now connect everything and rename this, rename this to reference RPM and this to the actual RPM. And this is the reference torque generated, and set the PID controller value. What the system will do, it will compare the reference RPM and the actual RPM through the PID controller, and the arrow signal will be generated in the form of torque. And rename the system to reference torque, and I'm giving a constant block which is a reference RPM as 500. Select another subsystem, delete this and add an input port, create a copy, paste, and add a mux, select for a function block, and add an output port. Connect everything. And rename the port as the torque, right? And rename this as flux. And this is IQ. And here we have to give one expression which is this. What the system will do, it will compare the torque and the flux value in this expression and give the IQ value. Let's rename this system as IQ calculation, and now select another subsystem in order to form ID value. Delete this, add an input port and add an gain block and add an output port. Connect everything. Now rename this port as Flux and this as ID. And in this gain block, keep the following expression. And give a constant flux value as 0.96 as my reference, and rename the subsystem as ID calculation. Now add another subsystem, rename this as theta calculation. Delete this one. Add an input port. Yes, and rename this port as 3. And this is the IQ value. And rename this port as Flux. And add a mux. And add a function block. And keep the expression. Click OK. And add a gain block. Paste it here. And add another input port. And rename as actual RPM. Add a sum block. Change to rectangular type. Now add a discrete time integrator and add an output. And rename this as Theta. And connect everything. And rename this gain as 2. And change the sample time. What this subsystem will do, it will compare IQ and flux value in the following expression, and it will then sum up with the actual speed and not to find the theta value. Now create another subsystem. Delete this one and add an input port. Paste it here and select for ABC to DQ converter. Now select for a demux. And select for an output port. Connect everything. and rename this port as the stator currents IABC, and this one as well as theta, and rename the output port as ID, and this one as IQ. What this subsystem will do is it will convert IABC stator currents into ID and IQ current. Now create another subsystem. Select this and add an input port, then add a gain block, add a transfer function, and then an output port. Connect everything. Inside this gain block, give the expression and rename this as the constant LM. This is a magnetizing inductance. And in this, change the denominator value and the output, change the output port, rename it as Flux. And change the subsystem into flux calculation, and this one as well, ABC to DQ convert. Now create another subsystem and delete this one, add an input port and paste it here, and add a constant block, and now select for a box, change to number of ports 3. Now select for DQ to ABC block, and select for an input port, and then select for an output. Connect everything. And rename this as ID, and this one as IQ, and this is the constant value, and this is theta value, and the output is stator current IABC. And rename the subsystem as DQ to ABC. Now create another subsystem. Delete this one and add an input port, paste it here, and add a demux, connect to the port, change the port to 3, create an add block. Change the parameters to the signs minus and create a relay block. Connect all negative signs to the first port. And connect all positive to the second port. Connect this to the relay block. And then add a data conversion block. Convert this to Boolean expression. And add a logic operator, which is a NOT gate. And select for data conversion block again. And now convert this to double. And select for a mux. Change the input to 6. And then connect everything. And select for the output port. And rename this port as IABC. And this one is the values what we found, IABC. And this has a pulse generator. Sorry. And rename this block as pulse generator. Now we have to select bus selector and connect it to here and select the stator currents IABC. Select and remove these two signals. Click OK and select mux. Change the input to 3. Connect everything. And select another bus selector. Connect it to the output here. And then select for the mechanical output, select rotor speed and the electromagnetic torque. Click OK. Now can give connection to the rest of the subsystems like this, and pulses will go here. Add a constant block as an input torque over here. This is the actual rotor speed. Connect here, and the torque value, the flux, and the flux here as well. The rotor speed, the IQ value from here, and IQ here, and ID from here, theta from here, and now add a scope. And change the inputs to 3 and the layout like this. Click OK, and in the view add this legend, and then we have to, this is the complete circuit of the, this is the complete model of the induction motor by using vector control method. Now I'm going to explain about the subsystem in detail, the model what I've created before. Subsystems. This is the simulink model that I've created, and there are various other examples in the MATLAB library itself. You can go and check them out. The first one is ID calculation. Inside this there will be one gain block which having a constant value magnetizing inductance, and this is the flux reference I've given, and we know that ID is the ratio between flux reference and magnetizing inductance. So we use the gain block to multiply the flux reference with the constant. And the second one is torque. The reference speed and the actual speed are compared and sent to the PID controller through the sum block for generating the error signal. IQ calculation. The reference torque and the flux are substituted in the formula in order to find the IQ value. Theta calculation. The IQ and the flux values are substituted in the mux in the expression and sum up with the actual speed to find the rotor angle such as theta. ABC to DQ conversion. The rotor angle such as theta and the stator currents IABC are undergoes the transformation by using the transformation block. This transformation is known as Clark and Park transformation. And DQ to ABC conversion. This block is used to convert DQ to ABC, which is known as inverse Clark and inverse Park transformation. The stator current, which is actually coming from the motor, and the stator current which we found using the calculation will be get compared here in order to generate the pulses by using this PWM generator block. These pulses will go to the three-phase inverter, and this inverter will give power supply to the motor, and here we are given as input as torque constant. Now we are going to run the simulation. I've given a stop time as 2 seconds. Now we can run this simulation. Now you can see it is getting compiled. This is the final result of the simulation, and the first one is the stator current of the motor, and the second one is the reference speed that we have given, and the third one is the actual speed coming from the rotor, and the fourth one is the torque. As you can see, once the actual speed is getting stabilized at the 500 rpm, the current is also getting stabilized here.